I had a typical science education. In high school, I did some less than memorable science fair projects. I took physics in college. I took astrophysics in grad school. And then, actually, there's a huge program of students at Los Alamos. Los Alamos can have up to 2,000 students there during a year. I think it's the largest collection of students outside of a university in the country. And I was fortunate to be one of those students. I went there to finish my thesis at Los Alamos. And so I started working on a variety of different things. I was launching rockets out of white sands. I was doing solar research. And I was developing these imaging techniques, which is now a part of the Poetics of Light exhibit upstairs. That's a method to locate and image these burst of gamma rays that come from the birth of black holes. And I was lucky to have a sabbatical to Japan in, I think, about 1982. So I was in my young 30s then. And I was there to help build an instrument that Los Alamos was going to put on a Japanese satellite. And I noticed that there was a clash of cultures there in Japan. And one of the examples that really stuck out in my mind was that we were calibrating the satellite, and my Japanese colleagues would come in with a very well thought out plan. They knew exactly how they're going to set the settings of the instruments, what they're going to measure, and what they're going to observe. And I just wanted to twirl all the knobs. So this got me thinking, why were they approaching this, so differently than I was approaching it? And what I realized is that they were, following a really methodical scientific method. That you form a question, that you construct a hypothesis, that you set up tests to do that with an experiment. You look at that, you see whether you have to adjust your theory or not, and then of course you publish the results so that other scientists can check you. And I realized that this is probably somewhat based on a view of science like it's a tree. Where you have science as a base, but there's major fields like biology, chemistry, mathematics, and physics. In fact, you can see my education on there. I started in physics, specialized in astrophysics, specialized to high energy astrophysics, and then specialized to gamma ray bursts, these bursts of gamma rays that you get when a black hole is born. Well, in Japan, I realized that I was no longer using the scientific method. And actually, to be precise, I was no longer using the scientific method sort of to learn something or to discover something. That I would use it to prove something, and when I published papers, I would use it as the structure of the paper. But I was not using it to direct my research or to discover something. And I realized that my Japanese colleagues were very much using it to direct their research. And they had this vision that you add scientific knowledge at the tips of these trees. You add knowledge, for example, to the gamma ray burst. So, and I was thinking also of some of my work, the early work that I did at Los Alamos while I was a grad student there, and I was working on different topics. And these are very diverse topics. They don't seem like they have anything pretty much in common. I was working on the solar wind. There's these particles that come off the sun. And because of that, I got very involved in a particular type of math, Fourier transforms. For that work out of white sands, I was working on X-ray collimators. And these are devices that allow you just to look in one, like blinders on a horse. They look in one small direction. And from that, I was working on binary functions that just has ones and zeros in them. Meanwhile, I was also working on these bursts of gamma rays and X-rays that come from gamma ray bursts, and I was developing these X-ray imaging techniques. Well, I remember one month, like it was November, I think it was November 1978, that in that month, 2 different people called me up and said, Ed, on the X-ray imaging, why don't you use these special functions? They're called pseudonoise sequences. And I said, well, first of all, they've already been tried. I knew one of my colleagues had tried them and they didn't work. And I also knew why they would not work. Because I knew that they had to have some properties from the combination of binary functions and Fourier transforms. And I said, and that's impossible. You could never make a truly perfect imaging system from those functions. So I decided to just sit down and show that. I programmed it up and showed why they didn't work. But then I began to realize why they didn't work. And I realized it from some of these other properties. So this shows this concept that science is more like a rat maze. That there are discoveries to be made between topics. And if you think of science as just adding details to the top of a tree, you don't get this concept that what you really should be doing is studying very diverse topics, because the discoveries are actually between topics that people didn't even know were related. I mean, nobody would guess that imaging would be related to solar wind or related to bursts of gamma rays. So, science, I think, is more like a rat maze. And in this analogy, you have some paths. They're well lit, well trodden, but sometimes they have cracks in them that you have to sort of step over because it's a little bit fuzzy. It's not quite explained. But the assumption is, well, someday somebody will go back and figure that out. You're pretty sure of that path. But sometimes you realize some paths just don't work. That there's some crack that's not just a puzzle, but it becomes a crisis. And something is wrong with this path. And most importantly about this analogy with a science as a rat maze is that discoveries are usually in areas that people didn't even know were connected. So, for example, we're talking about time. Well, basic unit of time is the day. And I look around and yes, a lot of us have seen a lot of days. And we know what that is. The sun comes up, the sun goes down. The sun comes up, the sun comes down. And it's pretty clear the sun is going around us, and that's what makes night and day. And indeed, that's this explanation down here, that the sun goes around the earth. Now, you can have this other explanation that the earth goes around the sun, but that does not explain night and day. It might explain summer and winter, but it doesn't explain night and day, because in order to explain night and day, if we're going around the earth has to spin. Really? The earth is 24,000 miles around. It takes 24 hours to spin. That means we're moving 1,000 miles an hour. I mean, how many people think we're moving 1,000 miles an hour right now? Okay, I mean, there's no 1,000-mile-an-hour wind. When I ride a horse, I get a wind. Why shouldn't I get a wind when the earth is spinning? When I drop something, it falls straight down. It doesn't go off to the side because the earth is spinning. There's other problems too with this view. And one of them is this sort of concept of action at a distance. In the 1600s, people like Galileo, when he was giving his presentations, he didn't have a remote control. He didn't have something you could press and your garage door goes open. Your television channel changes. We are very used to what's called action at a distance. We can do something here and something that happens over there with invisible forces. And they had no concept, in fact they even thought it was impossible to have an invisible force, that everything had to be mechanically coupled to each other. So because of that, they said, no, you can't have the earth go around the sun. That the sun has to go around the earth because it's in this, they actually had a special material for it. You think of the ancients, they had 4 materials. They had earth, water, air, and fire. Well, they had a 5th material as well, quintessence, which is what was holding up the planets. And each planet and the sun and the stars had their own shell of this material. And it had to be a sort of a shell of something because things had to be mechanically coupled to each other in order to get some motion. So now, there were some, cracks in the pathway. For example, Mars, no matter how many epicycles they added to this model, Mars never quite worked. But lesser known is the fact that even the moon wasn't working right in these models. Everybody agrees the moon goes around the Earth. But in these models, the moon would actually change its distance rather substantially from the Earth. And of course, the moon is always about the same size. Well, what finally happened was Galileo built a telescope, and he saw the moons of Jupiter. And this was, a pivotal discovery. He may not have been the first one actually to build a telescope, by the way. Other people have built telescopes. I think he had the advantage of being able to use Venetian glass, which is some of the best glass in the world. But, he decided to look at these objects. So I don't think he was using some scientific method. And this is ironic because we usually attribute to Galileo as sort of the first scientist who really did use a scientific method. If you read his papers about balls rolling down inclined planes, they're very well laid out as a hypothesis, what he's going to measure, how he's going to measure, and some explanation for that. But I think what he was doing here was just curling the knobs. Think I'll look at these stars. Think I'll look at Jupiter. And when he looked at Jupiter, he saw it had four stars near it. And then he looked a couple days later and the stars had moved. And he realized that those are not stars, that there are moons going around another planet. Well, this really put an end to the idea that the Earth is the center of the universe. Because you can really only have one center in this view that there's these shells that are mechanically moved. So, but here you have another center of the universe, right? I mean, the shells that these guys are moving on would mess up the shell that Jupiter is moving on around the sun. So he concluded, we get a stop sign here, no, it's not, the sun seems to go up and down, but that's because we are spinning, and we're spinning at 1,000 miles an hour. Maybe someday that'll be explained. And also somehow we have to have this action at a distance. Well, let's think about this action at a distance. By this time, and now we're up to like the 1600s, not 1750s, I think, with Newton. And Newton was studying different topics. In mathematics, he was developing calculus. He was also studying mechanics. He was studying how things roll down hills and are dropped, just like Galileo was studying. And he was looking at trying to understand how the planets move. Well, he suddenly realized, in fact, there's the story that he was sitting under an apple tree. Notice he was not sitting there with a checklist with his scientific method saying, okay, I've made my hypothesis, I've formed an idea, and now I'm going to do an experiment. No, he was sitting there with a unique combination of knowledge. He had been developing calculus, he'd been thinking about how things fall, he'd think about the planets, and nobody realized those topics are connected. And of course, they're connected by, they're connected by gravity. And he came up with there's an invisible force, gravity, that not only explains how apples fall, but how planets go around the sun. So let's talk about time some more. Now we move forward in time to the late 1880s. And by this time, some really amazing understandings have been developed. One thing is that light is actually connected to magnets and static electricity and electricity. Because we now understand that light is a wave, although sometimes it acts like a particle. Physicists talk out of both sides of their mouth all the time. Well, let's think of it as a wave and realize that what it really is that there's an oscillating electric field, which makes an oscillating magnetic field, which makes an oscillating electric field, which makes an oscillating magnetic field, and that's how light moves. So this light that we see coming from these lights are actually an electromagnetic wave. And a lot of the properties of light had been developed. But then there's a very important experiment that was done. And let me tell you about that experiment. But first, let's go back to everyday common sense stuff, not this physicist stuff, but this common sense stuff. So here we have a scientist on a train, and they're going to fire a bullet, and she's going to time how fast it's going. By the way, this train is moving, but to her, she's just on the train. She doesn't really care that the train is moving. So the train moves, and she measures that the bullet moved 5 feet in 2 seconds. So she concludes that the bullet was moving at 2.5 feet per second. Notice these are very safe bullets. Meanwhile, a guy on the ground was watching this, and he said, well, yes, but I saw it move 11 feet in those 2 seconds. So he says, according to him, it was moving 2.5 feet per second. Well, the man on the moon said, no, wait a minute, you're both wrong. That bullet was moving at 1,000 miles an hour because the Earth is spinning at 1,000 miles an hour. So, but this is perfectly fine. There's everything here is common sense. The time is absolute, but speed is relative. That depends on how you're moving or how you measure the speed of somebody else. Okay. Well, these experiments that were done in the 1880s used like a flashlight with light. And now, since we talk out of both sides of our mouth, now we're going to call it a particle. And our scientist is again going to measure, how fast that light is going. And so she measured and moves this 5 feet in 1 tick of the clock. And that would probably be about 5 billionths of a second. And so she says, well, I take that distance, I divide it by time, and I get the speed of light. Well, our ground observer says, well, I saw it move 11, but I saw it move in a different time. I saw it move in 2 seconds, such that I also get the speed of light. And the guy on the moon, he goes, yeah, me too. I measured that, and I also got the speed of light. This is very counterintuitive. They really should have gotten different speeds, just like they got for that bullet. But there's something different about light. That no matter who or how you're measuring light, everybody thinks light is moving the same speed. So, in this case, time is relative. But c is an absolute. Everybody agrees on the speed of light. Well, this is where relativity comes from. The fact that the time is relative. Notice her clock has just 1 tick. His clock has 2 ticks. If he watched her, he would not only say that light was moving at the speed of light, but he'd say, well, as a scientist, she seemed to be moving in slow motion. Her heart was beating slower. Even the electrons in her atoms are spinning slower. Her time is just different. The time is relative and depends on how fast you're moving relative to somebody else as to what time you think it had. But what they do is that the distance and the time always works out so everybody agrees to this absolute that c is a constant. You always get exactly the same number, no matter how you measure it. Okay, well, how does that fit into our rat maze? Well, at this time, there was Einstein working in a patent office who realized that what we're seeing is that time and space are together. It's space-time. It's 4-dimensional. And what we actually see and sense is a projection of that onto our 3-dimensional world. But also notice that he was working in a patent office. And working in a patent office in Switzerland, where they are obsessed with time and obsessed with trains running on time. Some of the patents that he were reviewing were how to synchronize clocks. Okay? So here we have a guy who, again, had a special diverse set of knowledge. He knew physics, although he couldn't get a job in physics. And his day job was thinking about, well, how do you synchronize clocks? Well, you send out a beam of light, and when the light gets there, you say, okay, start my clock and start the next clock. But wait a minute. People don't agree on distances in time. So here's the one that had the insight that what we are is we're living in a four-dimensional world. So here's what normal people think about space and time, right? That there's space and there's separate time. And of course this is a two-dimensional surface, so I've tried to draw a three-dimensional surface there, x, y, and z. Well, now I'm trying to draw a four-dimensional surface, which you really can't do in even 3 dimensions or much less than 2 dimensions. So I've only drawn 2 of the spatial dimensions, x and y, and then time is another dimension. Now, notice you have to have the same units, right? The spatial dimensions are like in feet. Well, the time unit is also like in feet because it's scaled by the speed of light. Again, the speed of light comes in. So, because of that, we have x, y, z, and then also time, but time scaled by the speed of light. So Einstein published this paper 110 years ago, and as I understand it, sort of, as he's just finishing up the paper, he looked at another thing. He looked at that classic thing that physicists do. I can remember the homework problems. Billiard balls colliding with each other. And you have to conserve momentum, you have to conserve energy. And when you think about that energy, well, the kinetic energy is sort of a sum over the path of this change in what we call momentum, that is the mass times the speed divided by the change in time. Well, notice how time comes into this. I mean, time comes in the definition of that speed. Time comes in the definition of time. And so, to really evaluate that energy, as you're trying to understand how billiard balls collide with each other, you have to take into account that time is relative. That time in different moving frames appear to be different. So we have to take that into account. And Einstein did. And actually the mathematics is what kids learn in AP high school calculus. And what he discovered was that you're trying to collide these billiard balls together and they have to conserve energy and momentum. That the only way you can conserve energy was if the ball had energy even when it was standing still. Okay. That E equals mc squared. Even when the mass is standing still, it had some energy. Not only that, but it had a huge amount of energy. I mean, c is a big number. And c squared is even a bigger number. So, and of course, this is the equation that he's famous for. But it actually comes from this consideration of time, that time is relative, and as you try to conserve energy, you end up, the only way you can balance energy is say, well, the balls had a certain amount of energy even when they're not moving. You then collide them and they sort of bounce off each other. But most of the energy is actually frozen in the mass. In fact, I think of mass as frozen energy. During the Big Bang, a huge amount of energy was released. Some of that energy collided and made some mass, and the mass stayed there as frozen energy. So we are frozen energy. And so everything has this frozen energy. A paperclip. Paperclip weighs around 1 gram, and it has actually a huge amount of energy in that. Of course, it's made out of aluminum, so you can't really change it easily from mass into energy. But if you did change the mass of that paperclip, or the mass of my fingernail, into energy, you'd get, like an atomic bomb going off. That's about how much mass is changed into energy inside an atomic bomb. So there's a huge amount of energy stored in mass. And it all has to do with time and how time is relative. Okay, well, time can turn out to be weird. And one of the famous cases is the twin paradox. Okay? In fact, here we have 2 people about the same age. I would say 40-ish or so. So we have these two people that are 40 years old, and one of them decides to take a spaceship to another star. So right now you're 40, and in 20 years you'll be 60. Right? You're 40, in 20 years you'll be 60, right? I mean, of course. Well, so you get in a spaceship and you go to a star that's 10 light years away, and you're going to move very close to the speed of light, like 0.9999 the speed of light. So as a faithful companion, you're going to watch him for 10 years as he goes out there. And for 10 years, as he comes back. Okay, out for 10 years, back for 10 years, finally he comes back, you're 20 years older, he's only 3.4 months older.
I like that.
Well, of course, this makes you a cougar now. And in fact, as she faithfully watched him go out there and come back, he seemed to be moving in slow motion, right? Because his time was just going slower. His atoms were spinning slower. Everything about him seemed to be moving slower because he was moving. And he was moving very close to the speed of light. Now, this is a real effect. The GPS satellites need to correct for this. That the GPS satellites actually need to take into account that the satellites are moving, at 17,000 miles an hour or so, around the Earth. Well, what about gravity? Let's go back to gravity. Newton thought he understood gravity. It's a simple force. But there were some things that didn't quite work. There was pesky problems in that as well. And one of those problems was the orbit of Mercury didn't quite work. Okay, it was going around, but it was also sort of twisting a little bit too. And they couldn't, in fact, they even came up with other planets. At the time, people were observing the planet Vulcan. Some of you might remember the planet Vulcan from Star Trek, but at times people actually said, oh, I saw Vulcan is located here, and it's the planet that is pulling Mercury around. Well, finally, they never really found Vulcan. But meanwhile, Einstein was working on different types of math. He was working on multidimensional math because of his work in special relativity. And he was applying some of the concepts from special relativity that certain things everybody should agree on. And the difference is in special relativity, they're working just on speeds, and in general relativity, they're working on acceleration. And you get an acceleration, for example, when gravity pulls on it. Well, what he came up with was general relativity, which is this concept that it's not really that there's an invisible force of gravity, but that mass, like us, actually bends space. We bend the space a little bit, and it's these bent space interacting that seem to behave like gravity. Except you can get extreme cases. You can get the extreme case of a black hole, which is a large, dense mass, so dense that it bends the space, but that makes it denser, so it bends the space some more, which makes it denser, which bends the space some more. And you end up producing an infinite amount of space inside a very small area. So now we have four-dimensional space-time that's being bent into another dimension. That's a fifth, if we're keeping track, that's the fifth dimension now we're talking about. That's bent into this other dimension. And you get these strange things such as black holes. Now, the black hole, time is a very special part of a black hole because space and time are the same. I mean, it's another dimension of space. So one of the reasons why black holes are black is because the light would take an infinite amount of time to come out. So we don't see any light coming from it because it would take an infinite amount of time to come out. So let's think about some of these time discoveries that we've talked about. Galileo, by observing Jupiter, found that the Earth goes around the sun. Therefore, the only way you can explain night and day is the fact that we're spinning, at 1,000 miles an hour. Einstein realized that, well, time is relative. What that really meant is that we live in a four-dimensional world. And if you work that out, you realize things have to have mass all by themselves, even when they're not moving. And that's E equals mc squared. And finally, also Einstein again, that space-time is bent by the mass, and therefore black holes. Well, putting this into the context of how the scientific method is used, one view is that the science is like a tree, and you sort of use the scientific method to grow it. Well, in this case, in my experience, most of the discoveries are not made from the existing details. It's made from having diverse set of knowledge, that each scientist is sort of unique, that they study different topics. So I always advise my students, don't study what I'm studying. Don't just become somebody who's, learn the same set of topics. Go out there and learn different topics, because discoveries are found in unexpected areas where things are coupled together. So science is like a rat maze, and effectively you become one with the maze and then have enlightenment. In fact, when I ended my sabbatical in Japan, they wanted me to give a talk, and they probably expected it to be on radiation processes and strong magnetic fields. But instead, I actually gave a version of this talk where I said, well, some people think science is like a tree, and we've always used the scientific method, whereas I think it's like a rat maze, and what you really should do is become one with the maze and have enlightenment. This is my, my advice to them, and advice to my students. So Pasteur is famous for saying, chance favors the prepared mind. I would say, well, chance favors the diverse mind. And another thing that I always tell my students is that the reason we do research is to gain hindsight. Because a lot of times, after you realize these topics are coupled, you go, well, of course the reason a rock falls to the ground is the same reason why the moon goes around us. So in my experience, scientific creativity is achieved through having a unique combination of knowledge and then intuition. In fact, the greatest compliment you can typically tell a scientist is that they're very intuitive. Now, some would think that, well, because they know a lot of equations. Trust me, I don't know that many equations. But more important is they have this diverse knowledge. And this is intuition. This is not intuition as to what the answer is. This is intuition as to what is important. Okay, thank you.